Next, we're going to discuss some of the characteristics that destroy differentiability. All right, so what that means is if a given function does not have a derivative in a particular place. So the three things that can do that are sharp turns, vertical tangent lines, or any kind of discontinuity in the original function. Right? Discontinuities in the original function should be pretty clear. If the original function itself is not continuous or it's not defined at a certain place, then we cannot take the derivative of that function in that place. So if we have a hole or a vertical asymptote or something along those lines, then we won't be able to take the derivative at those places either. Vertical tangent lines occur. A good example is a function like y equals the cubed root of x, which we can also write as x to the 1/3. If we were to graph that, it looks roughly like this, and we get one point right there at x equals 0 where the tangent line would have a vertical slope. Right? This kind of a thing we can see. It's kind of hard to really see it definitively in a graph. I mean, you can show it here and say, oh, the tangent line is vertical there, but it's really hard to tell whether it's really vertical or if it's just very, very steep there. What we can do, though, is when we take the derivative of this function, we would see that we get, if we tried to plug x equals 0 into that derivative, then we would get a number over 0 when we tried to actually calculate the derivative at x equals 0 in this case. And so we'll be able to see that a little bit later on in the chapter and examples that we come across. But that's sort of one of the more typical examples of a vertical tangent line, where we do have a continuous function, but we don't have differentiability there. And the other one that we come across is a sharp turn. Sharp turns come up now and again. Frequently they come up when there is some sort of a piecewise function, or oftentimes either a square root or something along those lines might come up, or a absolute value, something like that gives us sharp turns occasionally. So the important thing to remember is that just because a function is continuous does not necessarily mean it's differentiable. We may have a vertical tangent line or a sharp turn even if the function is continuous, but if we do have a discontinuity, then the function is definitely not differentiable. Right? And it works the other way as well. If f is differentiable at a certain place, then that function must be continuous there. All right, so let's talk a little bit more about this sharp turn. A lot of times you'll see a graph of it, and it'll be really obvious that there's a sharp turn right there. So we would say, if this was x equals c, then we would say this function is not differentiable at x equals c because there's a sharp turn there. So it's one thing to see it on a graph, and if you see it on a graph, it's usually made to look really obvious. It's clearly not a gradual transition from one slope to another. There's clearly a sharp corner there. But it's a little harder to see in terms of the function itself. So we could ask the question, and here in example 5, we're going to ask the question, is this function differentiable at x equals 3? So we're given this piecewise function, and we're asked if this function is differentiable. So the first thing we need to think about is this function continuous? If the function is not continuous, then it's not differentiable. We can stop there. If we find that it is continuous, then we have to check for a sharp turn and see if there's a sharp turn there. Okay, so let's take a look at what that means. So first, to check the continuity, it doesn't make sense for us to look at it as x is 3 because the piecewise function is separated at x equals 2. So we're going to talk about, is this function differentiable at x equals 2, not at x equals 3. Sorry about that. So we're going to check the function's continuity at x equals 2, and to do that we do it just like we did it back in chapter 1. We're going to say, what is the limit as we approach 2 from the negative side using this function? and what is the limit as we approach 2 from the positive side using 3x plus 3. And both of these limits we're going to solve just by a simple substitution. So we get 2 times 2 squared plus 1 is 9, and 3 times 2 plus 3 is 9. So yes, this function is continuous. And the next thing, when we look for a sharp turn, what a sharp turn means is if the derivative is different from the left and the right, then there's a sharp turn. And it doesn't matter by how much the derivative is different. All that matters is if it's different. So in order to not have a sharp turn, when we find the derivative from the left and the derivative from the right, they need to be exactly the same. All right, otherwise we have a sharp turn. So we're going to look at it from the left, and I'm going to use the alternative form of the derivative here so that it's an easier limit for me to evaluate. So I have, here's f of x, 2x squared plus 1, minus f of c. We found f of c in both cases were 9, so that makes our job easier here. So I have f of x minus 9 over x minus 2. Plus 1 minus 9 gives us a minus 8. I can factor a 2 out of there, and I have x squared minus 4, which will then factor x plus 2x minus 2. I can cancel out the x minus 2's, and then I solve this limit by substitution, and I have 2 times 2 plus 2, so I get 8. So the derivative of this function using the left side definition here, 2x squared plus 1, the derivative at 2 is 8. I'm going to do the same thing from the other side. 3x plus 3 minus 9 over x minus 2, the limit as we approach 2 from the positive side. Plus 3 minus 9 is minus 6. I factor out of 3, I have x minus 2. The x minus 2's cancel out numerator and denominator. I can all that's really left is the 3. I don't even have to substitute the 2. Right? So I see that from the left, the derivative at x equals 2 approaches 8. And from the right, the derivative at x equals 2 approaches 3. So these two derivatives are not equal to each other, so this is a sharp turn. All right. So this function is not differentiable at x equals 2 because of that sharp turn. All right. So that's what a sharp turn would actually look like analytically for us to kind of demonstrate that there's literally a sharp turn there rather than just being able to look at a graph where it's real obvious.